In this video, I'm going to go over the results section for finding the Kc of the thiocyanate equilibrium. I'm just starting here with the view of what you have at your lab bench before you start measuring the absorbances. So just a reminder that you have prepared 4 different trials and you have your standard solution, which is standard solution number 5. Now, the idea here is that we want to find the equilibrium constant. So we need the equilibrium concentrations of the iron ions in solution, the thiocyanate ions in solution, and the iron thiocyanate. And as we know, we are going to measure the absorbance. We did measure the absorbance of these solutions with the goal of using that information to determine the equilibrium concentration of the iron thiocyanate. So what we need to do in order to set up an ice chart is we need to first establish the initial concentrations of the iron and the thiocyanate in each of the test tubes that we had. And then we're going to use the absorbance information of our standard to determine a relationship between concentration and absorbance. And then finally, we're going to use that information to determine, based on the absorbance of our trials, the concentration at equilibrium of the iron thiocyanate. Okay, so that's a lot, but I think it's really important to have the big picture view in advance of starting your calculations. This is just a view earlier on in the experiment where you've got your iron solution at your lab bench and your potassium thiocyanate solution at your lab bench. You haven't been given the standard yet, and what you've done at this point is you've added 5 milliliters of the iron solution to each of the 4 test tubes. Now, just a reminder that what you did next was you took the thiocyanate solution and you added different dilutions to the test tube. So in test tube 1, you had 2 milliliters of the potassium thiocyanate and you diluted that to 5 milliliters. And for each of the test tubes following, you had a different dilution. Okay, so this table here summarizes those dilutions. Now, just a reminder, in your procedure, you were given just values to 1 significant digit, but you do want to, in your data, you want to make sure that you're reporting these values to the correct number of significant digits based on the instrument you use to make these measurements. Okay, so this is just a reminder of each of the trials, and what you need to do first, like we talked about, is determine the initial concentrations of both the iron and the thiocyanate based on the dilution. So you have the stock solution concentration of the iron, and you know that you took, in test tube 1, you had 5 milliliters of that stock solution, and then you diluted it to a total of 10 milliliters. So you're going to use your dilution formula in order to determine the concentration of the iron nitrate in that solution before the reaction began. Okay, so that's why we call it the initial concentration. So when I combined all of these substances, what was the concentration of the iron ions in the solution at that moment? You're going to do the same thing for the thiocyanate. Okay, so in the first trial, you had 2 milliliters of that stock solution of thiocyanate, and you diluted it to 10 milliliters. So you need to use the dilution formula to determine that concentration. Now, for the iron solution, the concentration is going to be constant, but for the thiocyanate solution, you have varying concentrations because you have varying degree of dilution. So for this one, you can do a sample calculation and then summarize your results in a table. The other thing to make note of is I'm kind of going interchangeably between referring to this as Fe3+, the iron solution, okay, and iron nitrate solution, or iron 3 nitrate solution. So why I'm doing that is because nitrate is a spectator ion. Okay, so we can use it in our conversation or not. You just don't want to be thrown off by that. Okay, so once we've combined our solutions, just a reminder that this is what we had. We've got a varying degree of intensity of the iron thiocyanate ion in the solution, and then we've been given our standard solution. So the next part here is to figure out what the concentration of that standard solution is so that we can establish our Beer's law relationship. And now this is a tricky bit of chemistry because iron 3 ions and thiocyanate ions will typically establish an equilibrium with the iron thiocyanate ions. Okay? And iron thiocyanate ions can only be made in situ, like in the lab. There isn't a solid form of this ion. We can only prepare it by combining iron 3 ions and thiocyanate ions. So we need to make a standard solution, we need a known quantity of FeSCN2+. And so the way that we did this was we prepared a standard that was made with 18 milliliters of this 0.2 molar iron 3 solution, which is significantly more concentrated than the solution we used in the experiment. And then the thiocyanate ions, we used 2 milliliters of that same stock solution. Okay, so the moles that I have here are given. I did N is equal to C times V, and I put my volume in liters to do that. So what you can see is that the iron, you can tell from the concentration above, but the iron is significantly in excess relative to the thiocyanate that's been put in the solution. Okay, so if we look at this in terms of an ice chart, these are my initial concentrations. So what I did here was I just found my concentration from my moles by dividing by my total volume of 20. Okay, and you can see here that again, the concentration of thiocyanate ions in solution is very, very small relative to the concentration of the Fe3+. So when we think about this system establishing an equilibrium, ultimately, our concentration of thiocyanate is going to have to go to 0. Okay? It's basically approaching 0, the limit as x equals 2 times 10 to the negative 4, and this concentration approaches 0. So what we can say about this is that the concentration of the iron thiocyanate in the equilibrium is 2 times 10 to the negative 4. Okay, to the best of our ability, and we've put such a large concentration of Fe3+ relative to the thiocyanate that we can be confident in this concentration of the iron thiocyanate. So now that I've got the concentration of the iron thiocyanate solution of 2 times 10 to the negative 4, and I have the absorbance of that solution, I can use that to find the slope of my Beer's law relationship. I have a point on the line of absorbance and concentration. This graph is in percentage, but we're working in molarity, it's fine. So the absorbance of my standard solution, which I recorded, is going to be used to determine the absorptivity constant, or the value for A. Okay, you can see here, I've intentionally put this here because there are different variables that are used for Beer's law. This is called epsilon. Okay, and L is the path length. Okay, our path length was 1 centimeter. So when we sub in our concentration and our absorbance into our Beer's law relationship, we are solving for A, or the absorptivity constant, which establishes a relationship between absorbance and concentration of the iron thiocyanate. And this is really helpful to us because now that I have the relationship between absorbance and concentration, and I have the absorbance values for my trials 1 through 4, I can now figure out my concentration of my iron thiocyanate in equilibrium of these 4 trials. Okay, so to kind of recap where we're at, we have our initial concentrations of our Fe3+ and our thiocyanate ions from our dilutions that we did. And now what we've done is we've managed to calculate the iron thiocyanate concentration at equilibrium. So now I'm ready to set up my ice chart and ultimately solve for the Kc for this particular equilibrium reaction.